Okay, welcome back. We were talking about different bonds, covalent bonds, polar, covalent, nonpolar, covalent bonds, ionic bonds, hydrogen bonds. You should be able to distinguish what those are. So if on a test I give you some bonds and ask you what they are, you should be able to pick them out. So now let's talk about water. And water is massively important to life. And it's got some very unique properties that make it very different than many other molecules out there. Make it unique. So, water likes to stick together. If you're ever in a swimming pool or in a lake, just kind of cup your hands and splash the water up. And you notice that they immediately kind of come together in these globules. Right, and they kind of land as these big drops, okay? And that tendency is cohesion, and that's because of the hydrogen bonds. Remember, there's hydrogen bonds in between the water molecules, and so that cohesion is much stronger for water than other liquid. You could take some rubbing alcohol and do the same thing, and it'll spatter as you toss it up and won't coagulate quite as much. And that cohesion is very important for plants. You get these redwood trees that are hundreds of feet high, and how do we get water from the bottom all the way up to the top? And that's cohesion. And so that water sticks together, and that helps bring it up the tree, fighting gravity. And so the tendency of two kinds of molecules to stick together is adhesion. So, same kind, cohesion. Different kinds, adhesion. And the cohesion is related to surface tension. Surface tension. So how hard is it to break those molecules apart? And so when we talk about water boiling, how much energy do we have to put into that pot of water before it breaks that surface tension, before the surface tension is broken? In fact, it takes tons of heat for water to boil. You can boil a pot. You can take a pot of sand and get it to 100 degrees Celsius far sooner than can the same amount of water. You can take alcohol has a very, very low boiling point compared to water, because water has that very, very strong cohesion. And it's those hydrogen bonds that give it that high surface tension. And you can kind of do this with a cup that's very still, and you can kind of lightly, very, very lightly touch it, and you'll see kind of the water bend, but you pull your finger out, it won't necessarily get wet. And so water striders kind of use that because they increase surface area, and they're so light that they don't push through that surface tension. We could walk on water if our feet were about 40 feet long, because we would have increased the surface area enough that the water tension would keep us up. So, hi. Hang on 1 second. I need to pause this. Okay, sorry about that. I apologize for that distraction. I'm not really sure where I was, so I think I just turned here. So we'll just kind of redo this whole thing. So the bonding, the hydrogen bonds in between the molecules of water, they resist temperature. This is why cities near the ocean have very calm climates. So I grew up in San Diego, and it has what's called a Mediterranean climate. So even though it's kind of dry, it's still near the beach. It very rarely gets above 90, and very rarely gets below 60. It just kind of stays in between that temperature. But where you think of here in Odessa, away from the water, it gets triple digits and drops down single digits. So there's a much higher fluctuation in temperature. And this is really important that you understand the difference here between heat and temperature. Some people will say that there's not enough temperature for metal to melt in certain ways. But it's not necessarily the temperature, but the heat, the energy that's involved that can create melting of metal when we're dealing with large scales and different things like that. So heat is the energy associated with movement of atoms and molecules. And temperature measures the intensity of the heat. So let me translate that because that's not written very well. So heat, or let's start with temperature. Temperature is how fast those molecules are moving. If they're moving slow, it's a lower temperature. If they're moving really fast, it's a higher temperature. Heat is the energy, or how many of those molecules are in motion. So if we take a huge boulder and a small pebble, they may be at the same temperature. The molecules there may be moving at the same rate or the same speed, but one has much more heat associated with it. So I kind of hope that clarifies heat and temperature. So heat's released when hydrogen bonds form. And then heat must be absorbed to break hydrogen bonds. So you think when you get out of the shower, when you're cold, those hydrogen bonds on your skin, it absorbs the heat of your body and turns into steam. Not necessarily steam, but turns into a gas. Well, that's kind of sucking off that heat from your body, and that's why you feel cold. But when you create hydrogen bonds, heat or that energy is released. Let's get my pen back going here. So one thing, speaking of getting out of the shower and that water cools down, is when the substance evaporates, what remains behind cools down, and that's what we call evaporative cooling. Sometimes houses use this in the desert. They use that evaporative cooling to kind of cool the temperature of the air. And it occurs because the molecules with the greatest energy leaves the surface. And this helps explain why when you spill water on your desk, you come back the next day, it's gone, even though it was never more than maybe 70 degrees in that room. We use cooling to cool down. And in fact, this was a big part of our evolution and one of the reasons why we lost hair, because we did hunting that required long stretches of running. And even today, they still kind of do that style of hunting where they'll stalk an antelope and the hunter will grab his spear and a jug of water and he'll take off running after the antelope, and the antelope of course will run away, but the hunter will keep going, the antelope will run away, and the hunter will use water to keep himself cool and sweat to keep himself cool, and he'll run after the antelope, and the antelope will slowly start to overheat and get to the point where it can no longer run anymore, and then the hunter will walk up to him and spear him. And the animal just can't even move because he's overheating. So water is interesting. It has three forms: gas, liquid, or solid. And this is a very odd property of water. It's less dense as a solid than a liquid. And this is really, really important. If you think about it, and if you have a lake, right, here's our lake. In the wintertime, it freezes. So if it froze from the bottom up, all the fish in there, let me draw a fish. There's my fish, well, a horrible fish, but whatever. All the fish in there would die. So if water was more dense than liquid, it would sink and all the fish would die when it freezes over. But it's not, and so all the water is less dense, and so it floats on the surface, and you get surface ice, and then you get your fish all happy as can be in the bottom of that lake. Well, not happy because lack of food, but whatever. It at least doesn't die, or not all of them die. So this is why ice floats, and so why we get icebergs on top and different things like that. So here's your graphic. When it's in water form, bonds are constantly breaking and reforming, and that's what makes it a liquid. There's enough energy in that water to keep it breaking and reforming. But when it becomes ice, it forms this very stable form. And so a solution is just a mixture. Salt and water is a solution. Excuse me. The dissolving agent is a solvent, in this case the water. The substance that is dissolved is the solute, the salt. An aqueous solution is one in which water is a solvent. So whenever water is a solvent, we can call it an aqueous solution. And so because water is a great solvent, and that happens because of the polarity, it pulls things apart, positive and negative charges. And so here's a picture. You got your sodium, your chloride, and the parts of the water that have the kind of positive charge kind of pull at the chloride, and parts that have the kind of negative charge pull at the sodium, and it breaks apart those salt crystals. So in the aqueous solutions, the small percentage of water molecules break apart into ions, and so you get some hydrogen ions and some hydroxide ions, and both of those are very reactive. And so when you have something that releases positive hydrogens into solution, it's an acid. And then the compound that accepts hydrogen is a base. So to measure this, we have what's called the pH scale, and it's logarithmic. It's important to know the difference between 7 and 8 is not just a scale of 1, it's a scale of 10. So pH scale, it describes how acidic or basic, and it goes from 0 to 14, 7 being neutral, 1 through 7 is acid, and 7 through 14 is basic. And so a buffer, you'll often see medicines, they use a buffer. And so when they put shots into your body, they use a buffer so it accepts hydrogen ions in excess and donates when it's depleted. They use that buffer to keep kind of the pH. And so here's a pH scale. Battery acid, very acidic. Lemon juice, acidic. Cola, tomato juice, those are all very acidic. Human urine is acidic. Pure water is at 7. Our human blood and tears are slightly basic. Seawater is past that, and then oven cleaners is extremely basic. And so the acidic solutions have more hydrogen ions, and the basic solution has more hydroxide ions. So when we burn our gasoline, our fossil fuels, we put in CO2 into the atmosphere. Then we have sulfur and nitrous oxides. They react with that water in the air, and they form acids. And then the acids fall back to Earth as acid rain. And we consider rain to be acidic when it has a pH lower than 5.2. And so the ocean will also absorb a lot of that CO2, which lowers the pH, because remember, seawater is basic. And so they call that ocean acidification. And so this is kind of how we get our acid rains. And here's coral reefs are very susceptible to ocean acidification. They need a certain pH. If any of you have kept a saltwater fish tank, you know the pH is crucial to life and keeping a good saltwater fish tank. And so the over-acidification is killing off reefs and limiting the number of organisms that can live there. And so this is a big issue you guys are going to have to deal with, and you're going to have to figure out what to do and what you should do about it. It's happening. It's very apparent that it's happening, but what to do about it, that's going to be your decision. So if you notice when we look at NASA lately, they're kind of big on the Mars rover, and what they're doing is they're always looking for signs of water, because water, the emergent properties, they support life. And so anytime they look at a planet through their telescope, they always ask, does it have water? Because if it has water, it's not only possible that it'll support life, it's very probable that it'll have some form of life. And so here's Mars rover, and it's taking soil samples, looking for bacteria and different signs of water. So here's a list of things you should be able to know and do. I have a couple questions coming up, and so this is chapter 2. So the first week it's chapter 1 and 2, and it's a lot, but 8-week courses go very quickly. So just be ready and don't fall behind.